We spent years focusing our load monitoring on high-speed running and total running demands. And we then started paying attention to acceleration a little bit more. But for a long, long time, deceleration was overlooked. Perhaps it was just dismissed as simply slowing down. But what if, in fact, deceleration was one of the most decisive and damaging load metrics that we could monitor? So this video is about why deceleration load deserves to be treated as its own variable. Often acceleration and deceleration metrics are coupled together, and it's felt that, well, however we're looking at acceleration metrics, we should be just mirroring that approach with our deceleration metrics. The issue is that mechanically, they are not the same thing. Both the frequency and intensity at which athletes across many team sports hit deceleration loads is actually greater than accelerations. Work by Damian Harper has shown across a whole mixture of different team sports, only in American football was the frequency of accelerations greater than decelerations. In every other sport, there were more frequent decelerations than accels. Furthermore, research has shown that athletes hit a higher absolute maximum deceleration value than they do in terms of their highest maximum acceleration. And it's not just this difference in the frequency and intensity, the actual movement demand is notably different. So one research paper found that soccer match load, the mean effort per meter was 28% higher compared to just normal running when accelerating, but as much as 65% higher when decelerating. We can also see just how high the forces are generated in a very short period of time when deceleration. In this figure, which is taken from the Science of Multi-directional Speed website, a collaboration between Damian Harper and a number of other practitioners and researchers, they've taken previous findings in the literature to create this illustration that really highlights the forces in those initial braking steps when decelerating from high speeds. They have been reported to be 2.7 times greater than initial acceleration, as 1.3 times greater than maximum velocity sprinting. Accelerations are a concentrically dominant movement demand, whereas the sudden braking demand involved with deceleration involve both eccentric muscle action as well as a quasi-isometric contraction. And it's these contraction modes that are capable of generating higher muscular tension than the concentric actions demanding of acceleration. Clearly then, braking is mechanically different to our acceleration and actually even more costly to the body. As we talked about, there are higher braking forces involved with deceleration demands, and so exposure to these demands can drive this cycle of fatigue into reduced coordination and therefore maybe increased tissue stress with more deceleration exposure. This figure also just highlights how fast those high impact forces are occurring within the first 10 to 40% of the stance, and shows that this must be rapidly attenuated then in a very short period of time. And that is very relevant to injury risk, when many injuries, particularly ACL injuries, occur in under 50 milliseconds, so within this time frame that we are talking about. So if we don't monitor deceleration distinctly and appropriately capture the demands of these movements, then we might be missing a key driver of injury risk. And the measurement and assessment of deceleration is something I'm going to talk a little bit more about in part 2 to this video. And it's so often the case that both injury risk and performance are related here, because it's not just about monitoring decelerations from an injury risk perspective, but actually decelerations matter in winning these team sports. Some research has shown that a deceleration was the second most common individual movement preceding a goal in the English Premier League in previous seasons. The capacity to decelerate can make the difference to key moments in games. And that's because effective deceleration enables higher approach speeds. It enables faster repositioning for both offensive and defensive actions. As I said, this higher frequency and magnitude of deceleration is often required around key moments such as goals in team sports. This ability to decelerate well is not purely down to strength alone. We can see this figure taken from the Braking Performance Framework led by Damien Harper, who I've already mentioned. And if you're doing any research into decelerations, then you need to read some of Damien's work. And perhaps this article is a good place to start with their Braking Performance Framework. Here we can see the neuromuscular and biomechanical determinant of horizontal deceleration ability and all these different factors that go into determining how well our athletes can decelerate. And again, I'm deliberately not yet talking about how to measure this because we're going to get into that in part 2. But in summary then, deceleration clearly is not just a mirror image of acceleration. It carries unique mechanical demands and consequently fatigue costs associated with this demand. So we should give then explicit attention to how we assess deceleration capacities and monitor deceleration load in our athletes. That then will be the focus of my next video. If it's already published while you're watching it, it will pop up so you can watch it next. If not, then certainly do subscribe so you don't miss out on part 2. These videos are all part of our athlete testing series sponsored by Val. So big thank you to them for sponsoring this series. And I look forward to seeing you again soon with another Sports Science Insights video.